Good morning, class. Today I wanted to talk about how you can do the analysis on your friction lab. So hopefully you've got a length and height of your ramp, or you used a protractor and measured the angle of the ramp, so you'd be able to use, so you should know the angle of the ramp, and you have a table for your times, your positions, and your velocities. And having your times and your velocities is of utmost importance for today, so you need to have those ready. So take them out, get them ready, and grab a laptop or a Chromebook because we are going to be putting this all together. Uh, the analysis here, these are some of the analysis questions that you can't do them until you have actually constructed the graph and determined the acceleration of the block. So the steps that we're going to go through together, you have to do those before you do the analysis. After which, on your next page, is the uncertainty analysis. And this uncertainty analysis, you will be able to see these instructions that I'm going over in a written format. So if you want to watch this video again, you can. But if you miss some things and you don't feel like going through the video again, you can just read the instructions right here. It goes through how to create the plot, how to get your best fit line, and how to create the functions that you're going to be taking the root mean squared analysis, or the kind of the average of the differences is the rough way to say it, to find your percent uncertainty for your acceleration slope. So that's the idea, and then that will hopefully, in combination with what we've been talking about, help us talk about how to do the uncertainty. So let's jump right into constructing things. First thing that we want to do is we want to graph it. Now we could graph things by hand, but that's going to be a lot of pain. What I'm going to do is I'm going to show you how to graph it with Desmos. This is doable in Excel. I'm not entirely familiar with all of the functions that are in Excel. For example, doing a line of least regression. I'm not sure how to do that in Excel, but I do know how to do it in Desmos. So that's what I'm going to show. So here we go. We're going to just make sure that we get into the graphing calculator part. And the first thing we need to do is we need to input our data. So up here on the top, we can add an item. We want to add a table. We can input an X and a Y table. You can rename these if you want. I'm going to leave them as X and Y. I understand that X is my time values and Y is going to be my velocity values. So maybe I'll relabel that as, no, I'll keep that. So with that in mind, my time values are easy. They go 0, and then 0.05, and then Desmos actually picks up pretty quick. You could just press enter and it'll autofill because it'll pick up on that pattern pretty quick. But your Y values, they don't. For one thing, I know it's like, ooh, you know, I don't actually have 0, so I'm going to cut 0. It's not part of my values. It's not part of my data. That's something is we shouldn't have a velocity for 0. But here are some values for velocity that I'm just making up. Your values are going to be different, but that's okay. Use this time to put in your own values. That's right. Do that to put in your own values. Oh, there we go. And now I put in my own values. But this would be a perfectly reasonable time to pause the video, make sure you have your values in. All right, coming back to it, I've made a table and that looks great, but none of my data actually exists on my graph that I can see. Well, it's because if I zoom out and I pull up, oh, there it is, and it seems to fit really close to on. Now that is a god-awful graph. This is terrible. All your data is in just nearly a vertical line. It's pretty bad. So I'm going to have to change the way I view this. Up in the top right corner, you have a graph settings, little wrench button. And here I have manual control over my axes. I'm actually going to put in, I'm going to label time in seconds. And why? This is velocity, and most of you likely did it in centimeters per second, which is fine. You're just going to have to do a little conversion later. what you can do is you can actually like write in the axes that you want. So maybe 0 will be my first time because there wasn't anything that existed, like it wasn't moving before 0 seconds. And I want to give myself a little space, so I'll go 0.65. Automatically, you can see it looks a lot better. I'm just going to make it look a little bit better. I see my smallest value is 30, so I want to be a little lower than that, perhaps at 27 or maybe even 22. And my highest value is at 110, so I'll be at 120. Looking at this, oh, hold on, no, my highest value is at 131. I cut off some of my data. I'm going to bump to 140. There we go. There we go. There's my data. It looks nice, and it looks, well, kind of linear for a bit, and then it's not linear at the end. And a good number of you might have data that looks exactly like this, where it's linear for a bit, but then not linear at the end. And we'll talk about what's going on there. But now that my view is nice, I don't want to screw it up by accidentally zooming in or out. So I'm going to go back in here, in the more options, I'm going to lock it. Now that it's locked, I can't zoom in or out. I'm trying to zoom in or out using my wheel, and it's not working. So it's locked, it looks good. You want to make it look good. You want your data to fit the entire graph first. Then you lock it. Do that, so you can see your stuff. Okay, so hopefully everybody has their view screen locked and everybody can see their data really well by now. Let's talk about how to put in the linear regression line, or this is basically the best fit line, but it's done by an algorithmic system. So I'm going to look, first thing I need to know is I need to know what I'm actually calling, because this is a function, this is actually an algorithmic program, so we need to make sure that we call specific variables. My headings here are y sub 1 and x sub 1. So these are the data sets that I am calling. So I'm going to start by doing y sub 1. And if you wonder how do you do sub, is you use the underscore. So y underscore 1, and then I'm just going to hit over on my key so you can see my cursor is no longer subscript. And then I want to use the tilde because that's the operation. Now I know that it's going to be the rest of the function of line is I have to use the slope, so I'm going to call m my slope, and then this is multiplying x sub 1, remember underscore there, and then I'm going to add b. And it has created a best fit line. This best fit line, the way it works is it uses a regression function, which means that it creates a line and then it algorithmic, and then it checks how far all the data points are away from the line, and it creates a new line, and it checks how far away all of those points are, and whichever one is better, it chooses that, and then it does the same function again, and it regressively, or like progressively gets closer and closer to the mathematically most appropriate value. And so this is the mathematically best value here. But looking at this isn't quite matching the data that I have. My data kind of follows a bit of a steeper slope, and then there's this thing that's tailing off. And so we have to ask ourselves, well, what even is this stuff that's tailing off? I think I'm like, wait a minute. The stuff that's tailing off, that is when the block had stopped and the tape keeps moving a little bit. When the block stops and then keeps moving, it's going to be slowing down. That's probably what these values are for. Oh, now unfortunately, I can't tell the computer just to ignore those points as I've done it now, because the computer isn't smart enough to recognize the situation. We the humans, are sufficiently intelligent to recognize this situation. So I am going to actually create a new scatter plot set. So I'm going to add a new scatter plot set. So notice how it's now x sub 2, y sub 2. I'm going to put in those points that I think are outliers, especially what I think are like these two here, 0.50, 1117, and so you can see I now have a purple dot over that. and 0.55, 110. And I make sure to do that because I want to ensure that I keep those on there because I'm not a liar. I measured those points, and so those points are going to be on my graph, but I am recognizing that these are outliers, and in my lab report I'm going to identify that I called these particular data points outliers for specific reasons. Now that they're outliers, I can delete them from my data set, and they're still preserved here in my second data set, but they're no longer part of the regression algorithm because they're no longer part of data set Y1 and data set X1, right? They're X2 and Y2, so they're no longer being used this way. This way, when I look at it, oh, this is a much better best fit line. It seems to be fitting my data really tightly. I have a little bit of variance, but that's expected because no measurement is perfect. This is a much, much better best fit line. So let's take a moment, everyone. Let's put in our best fit line, y sub 1, hit over, use the tilde, m x sub 1 plus b, and then also identify if you have any outliers. Create a second data table for your outliers, and then you can remove the outliers from your table data one. There are some people who are just like, oh, you know what, this one here seems to be pretty outliery. Maybe I'll kill that one. No, you can't just kill data points because they look bad. You have to have a specific reason. If anybody makes outliers of their middle points, you better have a damn good reason, otherwise I'm going to dock you marks for that. The reason I was able to count all these as outliers is because there was the specific reason. The block had finished moving, it was slowing down, that is no longer part of my measurement. That's the reason. That's why I can do it. No other reason. It has to be valid. So that's one thing that I want us to keep track of there. All right. Now that we have that, it's time for us to look at something called the residuals to help us see the uncertainty. You can see my best fit line doesn't fit perfectly with all my data points. There is in fact no line that will fit perfectly with all my data points. But there's this subset of data called E1. I can choose to plot it on the graph, though you'll see that it's not actually visible. I'd have to unlock my viewport and see, oh, here it is. It's these data points here. What these data points here are the level of variation, the literal, just the vertical distance that each of these data points is from the best fit line. That's what a residuals plot is. Now I need to redo things and make it look nice. Oh, sorry everyone. Okay, there we go. It's looking good again. So you don't actually need to plot your residuals data. I'm not going to. It's not a requirement. But that's what these values are. Now, we can find our uncertainties by manipulating these values. And the function that you'll use is right here. Your percent uncertainty will be equal to the square root of the function here is called total. What this is you're taking the sum of dataset E1 squared. So what this is doing is you're taking the dataset and you're squaring it. That turns all negative values into positive values. Then you can total it, you sum it, and then you divide by the number of data points, so you average it, so you now have the average of the squares, and then you square root. So you have the root of the mean of the squares, right? Root of the average of the squares, which is about the average. When you do that and you divide by the slope value you found, that would give you your percent uncertainty. So let's actually put that in. All right. So I'm going to call this value, I want to give it a name. I'm going to call it variable uncertainty U. I'm going to call it variable U for uncertainty. I'm going to make it equal to the square root, there we go. So if you're wondering how to do it, it's SQRT, square root of, and then I'm going to use a pair of brackets, the total, and notice how it went from italics variables to non-italics. That recognizes as a function. The total of bracket dataset E sub 1, and then I'm going to use the caret button. If you don't know what the caret button is, the little hat, it's Shift 6 on a standard keyboard, squared, end bracket. So you can notice here that I have E1 being squared, and then the next bracket takes place, which is the total function. And then that I want to divide by the number of data points. So I'm going to go ahead and look. What are my number of data points? I got 1, 2, 3, 4, 5, 6, 7, 8, 9. I have 9 data points that I didn't describe as outliers. So there's the 9. I close that. Now I'm going to hit over on my mouse, or sorry, over on my keyboard so I can divide the total function by my slope value. What is my slope value? Remember how we called m the slope value? It says it right here. My slope value, as I am reading it from Desmos, is 264. There we go. So u is my uncertainty value. My uncertainty value is 0.015. 0.015 is the same as 1.5%. So my data set has a statistical uncertainty of 1.5%. That's my statistical uncertainty. Now, I want to really identify a difference here. What we've done is we've used an algorithmic method of least regression, which means we need to be smarter than the computer. We need to analyze our data. We need to identify outliers because the computer can't do that for us. And then we used a statistical method. Notice this is just taking the difference from our things. This is just taking a statistical method of finding the uncertainty. There is no physics reasoning behind this. This is just my data seems to be this closely grouped is our argument. And that's fine so long as we are appropriately identifying that. So I've now been able to numerically and statistically determine the uncertainty of my acceleration. There's the uncertainty of my acceleration. Now that I have the uncertainty of my acceleration, and I can find the uncertainty of my angle, if you used a protractor, you just about how uncertain is it, and you just check from your ability to read the protractor. If you use the length and the height of the ramp, and you're using a sine, cos, or tan ratio, well then you are making a ratio or a division of your length and width, so you're going to add the percent uncertainties of those lengths and widths. Your absolute uncertainties for your lengths and widths should be in the range of millimeters, not particularly large, so not huge levels of uncertainty here. Now, when we're asking like, okay, what is our uncertainty of the coefficient of friction? You would go ahead and here, when you're using a net force equation, you should be able to solve for the coefficient of friction, break net force into mass times acceleration, gravity into mass times g, normal force into coefficient times, friction force times coefficient times normal force, and normal force, which balances gravity, is also mg. For step 2, this must all be in variables. Don't put any numbers in for step 2 here. When you solve for it, you'll notice that the only unknowns are the angles that you're using and the uncertainty that you're using. And if that's the case, well then that's really convenient. Those are the only unknowns, and so use the relationship of those. It is another ratio. You can add those percent uncertainties to get the percent uncertainty of your coefficient of friction, which is good. And then you'll report your coefficient of friction as a value with absolute uncertainty. That's what's going to happen. Okay, so that is how you create the graph. That is how you get the best fit line. That is how you use the residuals to statistically measure the uncertainty. But now you're like, Mr. Westgard, how do I figure this out? How do I get this into my lab report? Because my lab report is going to be something that we print out, or no, it's going to be something that we make ideally on the computer and submit it that way. So if you can log in, or you can log in just using anything, is you can save your graph. Make sure to save it so you don't lose your work. And second is you can click share graph here. When you share graph, don't feel like you should share anything as a link. I don't want any links. What I want you to export the image, and I can make it into a nice rectangle looking. Oh, that looks beautiful, right? That looks beautiful. I can choose line thickness if that's something that matters, and I can choose the file format. I recommend a PNG. You can download the PNG, and you can literally just insert your PNG into your lab report. If you're doing it on Word or Google Docs, you can insert those pretty easily using the insert image thing. If you're using something else like LaTeX format, you should probably know how that works because you're a few years ahead anyway when it comes to lab reporting procedures. So that's the mechanism in which you'll do. So there's little button here, and you can export it, and you can make it a nice little image. So that is how you can construct that. Then it's time, once you've constructed that, you've found your slope. Here it is. My slope is 264. That's great. It is time for me to start writing up my lab report. Your formal lab report needs to have a title, purpose, procedure, data analysis, uncertainty analysis, and conclusion. It needs to have all those points. The title, purpose, and procedure is super easy. It's this. Just copy this. Don't do anything different than copy this. Your data set, you're going to make something that looks like this, and you're going to put your data table underneath it. With your data table, what I also would like you to do is I would like you to put in the function of your best fit line. So make a little thing that they put on images where it's like figure 1. What are you going to do? Put some text just below your graph that has the function of your line. So you'd have velocity v is equal to, in my case, 264 t plus 18. Right, that's what I would just put that in there so it is explicitly stated. Then your analysis, just do these steps. Your uncertainty analysis, show your work, and here state what you've done. And the final part of your uncertainty analysis is I want you to report the coefficient of friction with its uncertainty in an absolute format. So it should be 0.5 plus or minus 0.1, for example. All right, that's what you need to do. And then lastly, you'll have a conclusion. The conclusion is a singular paragraph. It follows the structure. You write a sentence addressing the purpose. The answer should be yes, or the answer should be we found the coefficient of friction. That is what the whole purpose was, and you should have been able to do that. So the first sentence, we found the coefficient of friction between the block and the ramp. Recap your results. In other words, you would say, we found the coefficient of friction to be, and you literally put in those values. And then I want you to think about two sources of uncertainty that have not been addressed in our uncertainty calculations. So do not talk about uncertainty in the angle because we calculated for that. And do not talk about the uncertainty in your data set of velocities and how it's caused by some random error because we have addressed that in our calculations. So you have to be critical and think of sources of uncertainty that come from something that we were not able to quantify. Right, that's what it's about. And black or blue pen if you're going to do it by hand, but I strongly recommend you do it digitally. With that in mind, let me open up Teams for a second, is I've actually submitted. I've actually created a submission here for the formal assignment. You can view the assignment. Oh yeah, you're not going to see it this way. This is how I see it. The student view, there we go. I've put in both our lab sheet, and I've put in the grading sheet for you to view how it's going. Here's our formal lab sheet. So it is in, so you're going to be graded for the formatting. In other words, it is a formal lab report. You must make it a formal lab, do a good copy, don't slack off. I will be grading you on the data, the way that you're showing it, your formatting, and the your addressing of outliers. If you do have outliers that you've clearly identified and justified. There's marks for your calculations, for both your raw calculations and your uncertainty. There's questions for you about you doing the analysis and discussion. Sources of error unidentified. I think I might have changed that question. Calculating the coefficient of friction and appropriately calculating those. Yeah, so it's yeah, that one's just follow the analysis section, and then your conclusion here. Address the purpose, summarize results, address unquantifiable errors. Each point doesn't necessarily correspond to a point value, but it's related. So that's how it's going to be marked. That's how to do the analysis. And this is how you're going to submit it. Hopefully that answers everything that you have questions for. You might notice here that the due date is going to be March 13th. So that is a week and a half. We've got ourselves a full week and a little bit more. This is basically due when your dynamics test, where the 2D vectors test is going to be coming up. This is to make sure that you have made it a good copy. You do know what you're doing, and if you don't, you ask the questions before you submit it. Thanks everybody for giving me your time. Good luck. Have a good day.